One last talk before lunch. I'm happy to introduce Professor Yuyan Wang. She's Assistant Professor of Marketing at Stanford GSB. She has a unique and interesting background. She got PhD of Statistics from Princeton, and after that, she joined tech industry and worked for companies like Uber and Google 7 years as a machine learning scientist. So she studies recommendation systems. Today's talk is more about the recommendation system, the use of LLM in recommendation systems. Please allow me to
For a very kind introduction, and I just learned that I'm actually the extra thing before you at lunch, so sorry about that. And also, this is a little bit more engineering than the previous talks I have seen today, so there'll be some technical details on how to build a machine learning model, etc. I hope this is not too much as the last thing before the lunch. I hope this is still interesting. But as Kosky mentioned, I actually worked in the industry for several years before coming back to academia 2 years ago. And my research interest has been basically focusing on personalization and recommender systems and how do we better predict consumer preferences with large-scale machine learning models. So today I'm going to talk about one of our early works, actually still ongoing. We're still running experiments on this, on how LLMs can actually help recommender systems. And this is a joint work with Pan Li from Georgia Tech and Mingming Chen from Google. Okay, so recommender systems, I think everybody's already very familiar with this. So it's basically becoming increasingly critical to the success of many businesses today. So for example, I found these numbers online. So about half of the products sold on Amazon and 70% of the orders on Uber Eats are actually from their personalized recommendation engines. And on Netflix, this number is as high as 80%. So this is basically how important recommender systems are today. And then over the years, recommender systems have gained tremendous successes by leveraging big data and large-scale machine learning. Right? But then if you take a closer look at the systems that we have today, so they're essentially just gigantic black box models trying to predict the next item you're gonna buy or consume on the platform. For example, next product you're gonna purchase on Amazon or next video you're gonna watch on YouTube. And then in other words, these systems are actually not really capturing or understanding the why behind the consumer's preferences or choices. Right? Like why do you purchase a particular product on Amazon or why do you watch a certain video on YouTube? Like these black box models are simply not able or not built to basically provide insights into this why type of questions. And in other words, there's no transparency or explainability or interpretability with these machine learning models, and that's actually one of the major reasons why people hate machine learning sometimes these days. So actually, if you think about this topic, it's actually not a new topic of bringing, say, transparency or interpretability into machine learning models. So in fact, there's like very rich literature on explainable AI, which is readily applicable to recommender systems. So just a little bit of background, there are basically 3 families of methods in incorporating explainability in machine learning or in recommender systems. So the first group basically involves what we call post-hoc explanations. So basically this involves explaining an already trained machine learning model. Like after it's being trained, we do some post-hoc inspection, analysis, etc. to try to understand it. And then the second group involves intrinsic interpretability built into these models. So basically, these are like the white box approaches where you force your model to be interpretable at the beginning of the model building. Say if you force it to be linear or additive, etc., those are called intrinsic interpretability methods. And then the last group of methods is called supervised explanation training. So basically, they rely on ground truth explanations that's already generated or collected beforehand, and then you train the model to generate explanations on the fly. Okay. And then if you take a closer look at these 3 families of methods, so the first group, actually these post-hoc methods do not improve or help the model performance because it's done after you train the model, right? And it's not actually always reliable. Actually, like one of the faculty members here at Yale, like Tom and her co-authors have done really great work in this area. And in particular, in one of their recent works, they actually show that post-hoc methods are actually not that reliable always. And the second group methods, actually, there's also a lot of research also within the marketing community as well that basically shows that if you force your model to be interpretable, then it usually hurts the model performance. So basically, it's a trade-off between the accuracy of your model and the explainability of your model. And then the last group of methods is very obvious that if you want to generate some explanations, then you actually require human-curated explanations, which is costly, and also it's actually not clear how this additional curated explanations are actually helpful for your models. Okay, so in other words, there's always a price to pay for the explanations we're having today. So the natural question we want to ask is, well, are there actually any values in these explanations in improving the model's performance? And if so, how do we do that? Right? Because existing research hasn't really shown the value of explanations in improving these models. So actually, sorry. Does it work? Okay. Yeah. So actually, one of the key observations that motivates this work is everybody already knows that LLMs, or its impressive reasoning capability of these models. So for example, it's just a very toy example like I played with maybe like at the beginning of this project. So we basically tried whether LLMs are able to generate convincing explanations for why the consumer may or may not like a product. So for example, this is a hypothetical situation where never mind, so it's on the left here. So we basically asked LLMs to, given a particular purchase history of the consumer, so in this case, she bought apple, orange, pear, watermelon, basically a couple of fruits, and then the current product interest is an orange juice. And I also included some seemingly irrelevant details. For example, it's in a paper box with a sign in the logo, etc. And then I asked LLM to basically give an explanation of why this consumer may purchase this product, which is a positive explanation, and why this consumer may not purchase this product, which is a negative explanation. And you can see in the positive explanation case, the LLM is actually able to identify the link between orange juice product and the whole fruit orange, and saying that this is the reason if the consumer wants to buy an orange juice product, is because they like oranges in their past. And then in the negative explanation case, they're able to actually identify the differences between the orange juice and the orange product, which is the juice is a processed product, but the orange product itself is whole natural fruit. So this could probably be the reason the consumer does not like the orange juice product. So we can kind of have a feeling that these kind of reasoning or explanations are actually not that obvious if we simply just rely on consumers' past purchase history data to predict their preference. And we're trying to see that why this kind of reasoning can actually help the system more efficiently or more robustly learn consumer preferences. Okay, so this is basically our research question here. So can LLM-generated explanations for their reasoning capabilities be able to improve the performance of the black box recommender systems? Okay. And then a little bit technical details. Actually, this is not an easy thing to do, and it's not as easy as it seemingly would be. Because the first thing people have in mind will be, what about let's just use LLMs to make recommendations directly and maybe ask for explanations along the way. Right? So actually, it turns out that LLMs themselves are not good recommender systems. So in fact, I work very closely with industry recommendation platforms these days. Like none of the companies I talked to so far are able to use LLMs to replace their existing deep neural network-based recommender systems, simply because they still underperform those existing systems. And why is that? So this is my own summary of why they're not working. So I think the first reason is because these LLMs are actually designed to do generative tasks, meaning that they're generating text or generating images, etc. But recommender systems, intrinsically, is a discriminative task, meaning that among a set of items or products, I want to distinguish which are the ones that the consumers like more. Right? So they're intrinsically different tasks, so as a result, LLMs are not directly suitable for recommender systems. And as a result, people find that this deep neural network-based machine learning structure are still very, very useful in terms of exploiting the correlational patterns in your past consumption history and then make predictions accordingly. Okay. And then the natural question to ask next is, how do we basically incorporate this unstructured natural language text into the design of a deep neural network-based recommender system so that it can basically leverage this reasoning? And there are actually some existing solutions for leveraging LLM reasoning in recommender systems already. But again, if you take a closer at those works, so people either are proposing to use LLMs directly as a recommender system, while acknowledging the fact that they still underperform the state-of-art machine learning or deep learning-based recommender systems. or they actually basically force the LLMs to be structured now. So instead of natural language text, they are forcing the generated output or the reasoning of the LLMs to be in a structured graph so that it can be more easily leveraged by the existing machine learning architecture. Okay. So in other words, we think these are actually the unanswered questions from existing literature that we're trying to see whether we can answer them. So can LLMs be actually combined with deep learning-based recommender systems in order to improve the performance of these systems? And in particular, how do we incorporate this unstructured natural language text into the design of these structured machine learning models? Okay, so a little bit of engineering details just for people who are really tech savvy. So this is usually what the recommender systems look like today. So basically you take consumption history of the consumers and also what we know about the product, the context, etc. as an input feature, and everything goes through a black box machine learning system which generates a predicted outcome. For example, like a predicted rating of the movie, which will be used to rank the products or the items accordingly. Okay, so what we're proposing on a high level is to basically introduce this explanation generator that is trained based on an LLM that generates natural language explanations, but we also embed them into the structure of an existing deep neural network-based recommender system, so that in the end, what we're hoping to get is these explanations can directly help the learning of the recommendation tasks themselves. And also, the other kind of dotted arrow is something we're working on right now in the experiments, which is to see how the outcomes of the recommender system directly can be instructing the design or guiding the design of the generation of the explanations, right? So it's kind of like an organic loop between these two things. And then just a little bit more technical details, I guess I'll skip over this. So it's basically how do you implement this in a machine learning architecture, and this involves some pre-trained LLMs with some fine-tuning architecture, and then everything together we combine with a deep neural network-based recommender system. Okay, too much technical details. But let's look at some examples. So this is what we mean. So basically, given the consumer's past consumption history, so like in this case, it is restaurants. So you've been to this many restaurants in the past, and then now we have a candidate restaurant, which will also leverage LLMs to augment its profile, so it has like a more nuanced description of the restaurant. And then we ask basically, by leveraging this explanation generator that we built, we're able to generate both a positive and a negative explanation about why this consumer likes something, like this restaurant, or does not like this restaurant. And then the attention value is something I'm going to talk later. It's basically the amount of attention or focus that this model puts on each type of the explanations. And you can see in this case, the model puts more attention on the negative explanations. And indeed, the actual rating for the consumer is actually 1, like on a scale of 1 to 5. So it's like a low rating, and the predicted rating is actually close to that. Okay, so that's basically like a case study or like a workflow of our framework. And then, so I actually come from like statistics background. So I actually was interested to see like why this would potentially work, right? So we need some theory or some fundamental understanding to explain why LLMs can help the learning. So we can actually explain this a little bit by leveraging high-dimensional statistical learning theories. So let's, for example, say use S star to denote the subset of the important variables that are driving the consumer's decision-making. Right? For example, there are so many characters of this product you're considering when you're making a decision, but there may be a few of them that are very important and are critical in driving you to make the decision. So let's call that S star. And then we're able to actually leverage some theory to show that, first, LLMs are actually able, or they are likely to have better knowledge of the S star than the training data itself. Right? So written in statistical language, basically saying that this has probability going to 1 that is going to recover the true set of important variables. And the intuition behind this is because LLMs in their vast training data are likely, have likely seen some similar decision-making scenarios in the multiple environments in the past, right? So in this orange juice purchase example I showed you, in our training data, it's only orange juice purchase maybe on one platform. But in the training data of the LLMs, they're likely to see those purchases from, say, supermarkets, from online marketplaces, or offline stores, etc. So likely they have seen this from many, many different environments. And then statistically, by leveraging a theory called multi-environment learning, we're able to show that in this case, your model will be more likely to identify the truly important or the truly relevant variables. And then intuitively with that knowledge, a better knowledge of S star, it actually leads to better model convergence, better model performance, etc. So basically there's some convergence rate results we have there. It's basically saying that now with the knowledge of this S star, which is enabled by LLMs, your model now has faster convergence and lower generalization error. Okay. Sorry, a little bit maybe too much math right before lunch, but I hope this is still a little bit insightful. Okay, now I think comes the more exciting part of the project, which is some real-world results. Okay, so we're able to conduct some experiments on real-world recommendation data sets. And in particular, there are like three kind of benchmark data sets people use in recommender system community to evaluate their algorithms. And these are the TripAdvisor dataset, which is for hotel recommendation, and Amazon dataset, in which we look at the movie and TV category, and the Yelp dataset, which looks at restaurant ratings, etc. So basically, the goal for a recommender system is to basically predict the ratings for the products or the items in there, and then you'll basically rank according to the predicted ratings. And then in terms of the baselines we compare against, so a bunch of them, I won't go into details, but basically you can imagine them as the state-of-art methods for people doing interpretive recommender systems or sequential recommender systems or LLM-based recommender systems. Okay. And I'm also not going to overwhelm you with all the numerical results, but the message here is that our proposed method actually, significantly improves the performance compared with the group of state-of-art baselines. And they're at a scale of, say, 3% to 30, all the way to 30%. So this, to give you a sense of this is actually a huge improvement, because usually on the large-scale platforms we're having today, even a improvement in the percentage of, say, 0.0% something in the model accuracy can actually have the potential to translate to significant business metric ways. So we're actually not looking at like a trivial metric improvements here. They're actually very significant improvements. And then to basically demonstrate the statistical learning theory that I just showed you there, so theory suggests that our method should improve learning efficiency, meaning that with the same amount of data, your model should perform better. And so in this case, we're actually able to show that using only 25% of the training data, our method is able to match the best baseline's performance. Right? So it's basically an increased learning efficiency of your data. And then, we're also trying to understand, why or how this framework is helping recommender systems. So intuitively, we're incorporating the why or the reasoning behind consumers' choices into the system. And this kind of reasoning should intuitively provide, greater benefits to the examples that are harder, where the consumer's decisions are less obvious. Right? So it's those cases where the explicit understanding of the reasons behind their choices would intuitively be more helpful. And then how do we measure hardness? So statistically, you can measure this by so-called prediction uncertainty, which you can think of this as like a disagreement across different models. And this can be used as a measure of prediction uncertainty. And then we're actually able to see that the performance improvement of our framework actually is positively correlated with the hardness of the examples, meaning that if the decision-making scenario is harder, it's less obvious, then this reasoning framework actually helps more. Okay. And then I think last analysis we have here is the model's attention or focus on the different types of explanations we incorporate in this framework. So recall that we have both a positive explanation and a negative explanation. And in this case, we're able to basically measure on the aggregate level how much attention our model is paying attention to different types of explanations. And the learning here is that the model is actually focusing more on the positive explanations for examples that have positive outcomes, like high ratings. And they are focusing on more negative explanations for the examples that have low ratings or lower or negative outcomes. Right, so basically, this is mirroring how humans justify the decisions as well, right? So if I'm given a high rating or even purchasing something, then I'm thinking about the positive reasons why I like this. And if I'm not purchasing something, then I'm actually thinking about the negative reasons why I don't like this. Okay. And then I think I'm out of time. I'll have 5 minutes. Oh, great. Then I'm actually going to zoom into a little bit more understanding here. So we all know LLMs are like so capable of doing everything, right? So they're capable of doing math, reasoning, or just generating augmentations of the profiles to get a better understanding of everything in the world. So how do we know that this performance gain that we just observed from all experiments is actually from their reasoning capabilities, not something else? Right? For example, some alternative hypothesis could be that they actually maybe have already seen this data set that we use in our experiments. And maybe they already have some external knowledge about the data set. So they're just memorizing the results instead of trying to do the reasoning and then do the predictions accordingly. Or some other alternative hypothesis could be it's actually just their summarization skills, right? They're just better at summarizing or doing feature engineering of the consumer's past consumption history, and as a result, it's just a more efficient or better feature processor. Right? So how can we show that it's not those that are benefiting this framework, but rather the reasoning capability in particular? Right? So the first evidence we have here is the fact that the LLMs with stronger reasoning capabilities actually use larger gains in our framework. So we have several tables showing you that, but I'm just gonna verbally summarize the results here. And so we have like a reasoning capability leaderboard that people built, which basically shows you among like the dozens or couples of dozens of language models we have today, which ones score higher on the reasoning benchmarks. So we basically find that if we use our framework with those different LLMs, then the LLMs that are ranking higher on these reasoning benchmarks are also get better results, the recommendation results from our framework. So this is kind of like a set evidence that why reasoning is helping here. And second, we actually also use LLMs to do profile augmentation, which is to generate more understandings of each product in the data set. And we found that profile augmentation is actually not the key driver, because when we remove all this LLM augmented information in the framework, it still leads to a good results. And also in one of the data sets we looked at, we use actually an old LLM that is trained before the generation of the data set. And we see that in this case, there's no way that they can memorize this data set or have any external knowledge about this data set, but the gain is basically still at the same scale. So that's why we think it's actually not their external knowledge that's helping here. Yes?
Yeah, so I had a question. So my understanding with recommendation systems, traditional recommendation systems, that one of their weaknesses is that they're looking at like correlation patterns, and they're not saying anything really about like the causal mechanisms. And so I'm wondering, with what you have here, should I interpret this causally? Like if you look at the outputs of what your LLM model is saying, and it's saying, hey, this is a key driver of the result, is that a causal claim?
That's a great question. Actually, I wanted to claim that, but I don't think I'm comfortable claiming like that. So you can imagine, you're definitely right. So if we're actually able to get the whole black box system closer to the true causal mechanism or the true data generating process of the whole thing, then intuitively this will be a more robust, more accurate system, and it's gonna perform better, right? So that's definitely the intuition. You're exactly right. And it's the motivation for this work, which is incorporating reasoning into the system, is actually motivated by that. Because we are trying to see having some deeper understanding about the data generating process could help. But the reason why you didn't see any causal or causality terminology in my presentation is because we cannot actually validate that from this work. Right? So we're not able to collect ground truth decision-making process of the consumer or directly ask them, these are actually the three aspects that you considered when you're making the decision. We do not know that. Right? So we can only say, like statistically, that we have those theorems showing that if there are actually some ground truth mechanisms there, which is the S star, the LLMs have a higher chance of probability converging to 1 to recover them given infinite amount of data. Just statistically speaking, that could be the case. But in reality, we cannot actually validate that causal claim. Yeah, so that's why I don't say like this LLMs getting us to the causality, but rather just their reasoning that somehow gets the model learn more efficiently. Yeah, but that's a good question. Okay. So the last point I'm having here is, so people actually also may wonder, why is it reasoning? Maybe they also have other capabilities that also can help the learning here. So for example, it's just a feature processor. It's a better feature engineering method. Right? So I'm just asking LLMs to help me identify the best summarization of the user history so that it helps the model learning. So we actually try that as well. So simply by replacing the term reasoning with summarization in the prompt of our LLM-based explanation generator, we actually found that the results perform significantly worse. Right? So that basically means that if you ask for a summarization instead of a reason, then the model suddenly does not think this is useful anymore. Right? So I think this is another side evidence that it's actually the reasoning capability that's helping the performance here. So to conclude, so in this one, we actually propose engineering or technical framework on how do we use LLMs to help deep learning-based recommender systems. And we have empirically validated that on some real-world benchmark data sets, and also provided some statistical foundations of why LLMs can potentially help here. And then in terms of managerial implications, I think this is the interesting one because we actually tried really hard to look at existing explanation or interpretable AI literature, and it seems that very few people actually, none to our knowledge, that actually talked about how explanations themselves can actually help the performance of the black box systems, rather than creating a trade-off or just not touching the model at all. And in this case, we're trying to provide some evidence that actually explanations are helpful. And also, both positive and negative explanations are essential because we also did some ablation study that if we remove one of them, the performance is not as good. And this may actually shed some light on the value of interpretability in a recommender system design because a lot of the firms today are actually thinking that it's a trade-off. Like if you provide this interpretability, then it's going to hurt the performance. And we are potentially providing one way to actually contribute to interpretable recommender systems. And then in terms of next steps, as I mentioned, we actually wanted this whole thing to be an organic loop in the sense that not only explanations help the recommender systems learning, but also the recommender system learning itself can actually guide the explanation of guide the generation of the explanation itself. So that in the end, it's like more like an alternating training loop, so that in the end, you have the optimal explanations and also the optimal recommendation performance. All right, thank you.
We can do one question.
Yes.
Hi. Yeah, thank you so much. That was a really, really awesome talk. Of course, like XAI is really vital nowadays. So I'm curious how far you think you can take your work. Like specifically, do you see this as a potentially model agnostic way of doing explainability? And do you see you being able to extend this to far beyond just recommendation systems, but like a lot of other ML architectures?
Yeah, that's a great question. Thanks. So I think I would like to say yes to both questions. The first one, we do think it's model agnostic in a way that if you look at closely the model architecture design, so we actually embed the generated recommendations as the generated explanations as embeddings, which are then combined with a deep neural network-based recommender system. But then how do you design a recommender system? Like how many layers are there? Like where you use a transformer or not, etc. Those are actually independent of this embedding block that we design. So in that sense, we think it should be a model agnostic. Yeah. The only challenge I think is basically how comfortable you are with calling an LLM for every single candidate in your whole recommendation data set when you're generating recommendations. And for that, we also have some mitigation discussions in the paper because the explanations does not need to be generated on the fly. It can actually be generated like right after each purchase of yours in an offline fashion. So that in this case, you don't need to actually call an LLM for every single possible candidate, like on the fly in real time, because that's definitely not feasible. Yeah, and then to your second question, I also wanted to showcase that this is actually, thank you for bringing that up, one of the generalization discussion we want to have, which is this actually shows an organic way to basically combine unstructured LLMs with structured deep learning machine learning models, because people are not usually thinking of a way like how do you basically combine structured versus unstructured together in one framework. And what we're showing here, potentially with this like alternating training loop we're still working on these days, is actually one way to basically organically combine unstructured data and structured machine learning design. Okay. Thanks for the question. Happy to talk more about that.